Jai Hind, welcome to the course Network Analysis and Synthesis, and today we are going to discuss about the network analysis of RL, RC and RLC circuits using Laplace transform. Of this content are network analysis of RLC, RL and RC with and without initial conditions. The circuit may or may not have initial conditions. So, how we will do? And then evaluation of initial conditions. If the circuit is given and you are required to find the initial conditions or final conditions of the circuit, so how we will get it? So these two topics I am going to cover today. Basically, in a solution of any physical systems, or you can say the any continuous time systems, can be described by the differential equations. And to solve a differential equations, earlier you used to have the classical methods. So in classical methods there are three steps: determination of complementary function, determination of particular integrals and determination of arbitrary constants with the help of the initial conditions. So there are three steps to carry out the classical method. The same differential equation can be solved by the Laplace transform. Then the question arises, why we go for the Laplace transform. So there are some limitations in the classical methods. If the network or functions contain some discontinuities, functions and their derivatives contain some discontinuities, then it is very difficult to apply the classical method. So in that case we can apply the Laplace transform. So Laplace transform is a powerful mathematical tool to solve a differential equation. Okay, and what when we apply a Laplace transform to a differential equation, the differential equations become a algebraic equations, and algebraic equations can be solved by a algebraic manipulations. And in the last we just take the inverse of the Laplace transform in such a way that it becomes the solution of the original differential equations. So this particular integral is known as the force in response, and the complementary function is called the natural response. So there are two ways to obtain the initial conditions for a network, either through the differential equation describing the network or through the knowledge of the physical behavior of the R, L and C elements of the network. So basically that we will discuss in detail the second part, that is the part B, how we will evaluate the initial conditions of RLC elements of a given network. So what is the initial condition for a capacitor? For a capacitor, the voltage current relationship can be given as Vc 0 plus. 0 plus is the time at which we just apply the switch. After the switch, Vc this it is 1 by C, then 0 minus to 0 plus IT del T, and Vc 0 is the initial voltage across the capacitor. So this is the equation for a capacitor. So IT does not contain impulses or derivatives of impulses, Vc 0 plus or Vc 0 minus. So what does it mean? It means the impulse functions are defined at t is equal to 0, because an impulse function does not exist other than t is equal to 0. Its value is 0 other than t is equal to 0. At t is equal to 0, its value is infinite. So Vc 0 plus or Vc 0 minus is the time after the switching and prior to the switching. Okay, so impulses are 0. So there is no initial charge on the capacitor. So Vc 0 plus 0, when there is no stored energy in the capacitor, equivalent circuit is short circuit. So at t is equal to 0, the basic is the at t is equal to 0, capacitor behaves as a short circuit. So take a simple RC circuit, okay, and the switch is closed at t is equal to 0. So at t is equal to 0, capacitor behaves as a short circuit. So equivalent circuit at t is equal to 0 will be like this only resistive. So this is the equation of the ut RIT plus 1 by C 0 minus to T IT dt I tau d tau. So, this is the simple Kirchhoff's voltage law applied in the RC circuit. Okay. Now, VUT, UT is the unit step function which is defined for t greater than or equal to 0. So, for t greater than or equal to 0 UT is 1. So, simply it is V. For t less than 0 UT is 0. So, for t less than 0 V is 0. So, we can apply, we can write V into UT. Okay. So, after differentiating we get V delta t R I dash t plus I t upon C. So, if we differentiate a unit step we get impulse function. Okay. And we know that the impulse function is 0 everywhere at t is equal to 0 except at t is equal to 0 and at t is equal to 0 its value is infinite. So, V delta, so at t is equal to 0 plus this equation V delta t will be 0. So, the equations become 0 is equal to R I 0 plus I 0 plus upon C. So, I 0 is V upon R. So, this is the initial current through the inductor, we can say it is V upon R. So, this way we can find the initial current through the capacitor IC 0 plus. And I infinite is 0 because at t is equal to infinite the capacitor behaves as a open circuit. So, when the capacitor is open, the circuit is open, so I is infinite is 0. So, this way we can find the initial currents or final currents through a RC circuit. So, this is I 0 plus C V minus V upon R square V upon R square C. So, this way we can get. So, I dash is basically dit upon dt, I dash is dit upon dt. So, I 0 plus is V upon R and I dash 0 plus is minus V upon R square C. So, one is the current and the initial current and derivative of the initial current. So, the final current or steady state condition solution is obtained from our knowledge of DC circuit. We know that for a DC excitation a capacitor can be open circuit. So, IPT is equal to I infinite, that is particular integral 0. Come to the initial conditions for a inductor. So, we can write the equation for the inductor IL is equal to 1 by L integral V tau d tau plus initial current through the inductor. So, if Vt does not contain impulses, then IL 0 is plus is equal to IL 0 minus, and if there is no initial current, so IL is 0 which corresponds to an open circuit. So, current through the inductor can not change instantaneously due to conservation of flux linkage. So, when you just apply the switch, okay, inductor behaves as a open circuit. Because why it behaves as a open circuit? Because inductor opposes the rate of change of current. So, at t is equal to 0 plus it behaves as a open circuit, and the steady state solution for current is obtained through the knowledge that for a DC source. So, inductor is short circuit. So, simply at t is equal to 0 plus inductor behaves as a open circuit, and at t is equal to infinity means in steady state the inductor behaves as a short circuit. So, in summary we can write that the at t is equal to 0 at time of the switching inductor behaves as open circuit and capacitor behaves as a short circuit. At t is equal to infinity, when the circuit is in a steady state, the inductor behaves as a short circuit and capacitor behaves as a open circuit. So, these are the two important behaviors of circuit elements R, L and C. So, at t is equal to 0, how we can represent the inductor capacitor with and without initial conditions. So, at t is equal to 0, resistor is does not have any effect. So, it is same as R, whereas L is replaced by a open circuit. So, at t is equal to 0, inductor behaves as a open circuit, at t is equal to 0, capacitor behaves as a short circuit, and when the inductor carries some initial current I 0. So, this inductor can be represented by this circuit, open circuit, and then the current, and when the capacitor having some charge V 0. So, it is replaced by a short circuit and the voltage V 0. Similarly, we can represent the circuit at t is equal to infinity. So, at t is equal to infinity, inductor behaves as a short circuit, capacitor behaves as a open circuit, and if the inductor having some current, so it is represented by this. So, this is the short circuit, impedance is short circuit, so impedance is 0, basically this is the 0 impedance, and this is the current source, that is the current through the current having the initial current that inductor having, and this is the open circuit and the open circuit voltage V 0. Then before discussing the network analysis of RL, RC and RLC networks using Laplace transform, first and foremost just I am going to discuss element wise resistor, inductor and capacitor, and then we put these elements in the circuit and then carry out the analysis. So, this is the R is in time domain, Vt is equal to RIT. So, this is the time domain. In the S domain, transform impedance means from the time domain into S domain. So, this is the representation of a resistor in the S domain. Either we can write in terms of resistor or in terms of the conductance, resistance or conductance we can have. Then inductors. So, this is an inductor, the voltage Vt is applied and this inductor carries current I 0 minus. So, initial current through the inductor is I 0 minus and IT is the current through the inductor at time t. So, we can write the simple differential equation Vt is L dit upon dt, and we can similarly we can have the expression for the current IT. So, it is 1 by L 0 to t. Okay. Take the Laplace transform of the above. So, above differential equation. So, Vs is SLI, this is 0, this is 0, basically this is not 0, this is the bracket. So, SL, this is SL, IS minus this is bracket, this is like this, okay, minus Li 0 plus, okay. So, this is the, if you take the Laplace transform Vt is equal to L dit upon dt. So, Vs is equal to SLIS minus Li 0. So, if the element is given, we have applied the we have written the equation. So, now the equation is given, you are required to draw the circuit. So, this we can draw the circuit in this fashion, simple KVL. We apply the KVL here, we can get these equations. So, now this is the current variable ds upon SL, I 0 minus upon S. Okay. So, this is the current equation, this is the voltage equation. So, for this current equation we can have the circuit diagram. So, this is the circuit diagram and you can check here, if you apply the Kirchhoff's voltage law, Kirchhoff's current law here. So, Is is equal to I 0 minus upon S plus 1 by SL is nothing, this is the, if you take the admittance then it will be SL, otherwise the impedance. Okay. So, this. So, similarly we can have the two types of configuration for a circuit for a inductor in S domain. So, suppose a network is given, it is very convenient to apply the Kirchhoff's voltage law. So, what we will do, there we convert this inductor in this fashion. Okay. if the network is suitable for applying the Kirchhoff's current law, in that case that inductor in time domain can be written in this fashion in S domain. So, it is very convenient to use the Kirchhoff's current law in this and Kirchhoff's voltage law in this circuit. Similarly, we can have the expressions or circuit diagram in S domain for the capacitor also. So, this is the capacitor in time domain. So, Vt is IT and voltage across the capacitor is V0 minus. So, that is the initial voltage across the capacitor. So, just we can write the equations. So, IT is equal to C dVt upon dt and IT is equal to 1 by C 0 to t I tau d tau plus V0 minus. V0 minus is nothing but it is the initial charge across the capacitor or voltage across the capacitor. So, if we apply the Laplace transform on these two equations, we can get first this Is is equal to SC Vs minus CV0. So, this is the expression for voltage, and for this voltage we can have this circuit diagram, equivalent circuit diagram in S domain. This is the time domain, this is the S domain. So, similarly we can have the expression for the current. So, this is the circuit diagram for the current. So, here it is very convenient to apply Kirchhoff's voltage law, here it is very convenient to apply the Kirchhoff's current law. So, depending upon the network configuration, which law is appropriate, that way there we can modify the circuit accordingly. So, Is is equal to SCVS minus CV0. Okay. So, this is the just theoretical background of this topic. Now, we just go we just go through some problems, and the first problem is the switch is closed at t is equal to 0. Find the initial and final conditions, that is I0 plus di0 plus upon dt, matlab first derivative of initial current, and I infinite, that is the steady state current or final current. And it is given there is no initial current through the inductor. So, I0 is 0. So, this is the given circuit. In the given circuit, the switch is closed at t is equal to 0. So, at t is equal to 0 plus the inductor behaves as a short circuit. Okay, and then we can find the current through the resistor or inductor that we can get. But in the given question, it is also required to find the di0 plus upon dt. Okay, first derivative. So, it is better to write the equation for the given RL circuit for any time t, okay, and then differentiate it and put the time t is equal to 0 plus, we can get the value of di0. This way, if the first derivative or second derivative, so it is better to write the equations for any time t. So, it is a first order equation. So, we can have the only di0 upon dt. So, this is the equation, simple. When the switch is closed, so this is VUT. VUT is nothing but it is multiplied by unit function, and the unit function is only 1 for t greater than or equal to 0. T less than 0, its value is 0. So, L di upon dt RIT. Okay. So, at t is equal to 0 plus, the circuit becomes, so inductor behaves as a open circuit. Inductor behaves as open circuit because it opposes the rate of change of current. So, it behaves as open circuit. So, I0 is 0 because it is opened, no current will flow through the resistor. And so, V is equal to L di 0 plus dt of, and this I0 is 0. So, this is 0, this is V upon R. So, this way we can find the di0 plus upon dt, that is V upon L. At t is equal to infinity, the circuit becomes, so at t is equal to infinity, the inductor behaves as a short circuit. So, this is the equivalent circuit of at t is equal to infinity. So this inductor behaves as a short circuit. So I infinity will be V upon R. So this is V upon R. So the initial current I0 plus is 0 because at the time of the switching the inductor behaves as a open circuit. So current is 0, but we have the first derivative di0 plus dt, that is V upon L. So this way we can find the initial conditions of a RL circuit. This is another problem. The switch is closed at t is equal to 0. Find the initial conditions and final I1, I2, I1 infinity, I2 infinity, and first derivative of I1 0 plus upon dt. And it is given there is no initial current through the inductor. So this is the circuit consisting R, L and C. Okay. Now the switch is closed at t is equal to 0. So there is no initial current through the inductor and charge across the capacitor. So just this is the expression for any time t, BUT R1 I1. Simple, if we apply the KVL we can write these two equations for any time t. Now at t is equal to 0 the switch is closed. The switch is closed, so the equivalent circuit will be like this. The capacitor behaves as a short circuit and inductor behaves as a open circuit. So this is the equivalent circuit at t is equal to 0 plus when we apply the switching. Then we can find, so I1 is V upon R1 and I2 is 0 because in this is the open, so no current through the R2, so I2 is 0. Now to find the first derivative we just differentiate equation 1, so we get V delta t R1 di1 t upon dt 1 by C this. So at t is equal to 0 plus delta t will be 0 because impulse function is defined for t is equal to 0. Other than t is equal to 0 its value is 0. So V delta t at t is equal to 0 plus will be 0. So this equation becomes R is equal to R1 di1 0 plus upon dt I1 0 plus minus I2 0 upon C. So this way we can find the di1 0 plus upon dt and that is minus B R1 square upon C. At t is equal to infinity the circuit becomes, so at t is equal to infinity we know that the capacitor behaves as open circuit and inductor behaves as a short circuit. So this is the equivalent circuit. So current will be, so in this case there will be one loop, current will flow from V1 R2 R1, this is R1, this is your R1, this is R1 R2. So I1, so same current I1 is equal to I1 infinity is equal to I2 infinity, it will be equal to V upon R1 plus R2, simple. This way we can get initial and final conditions through the inductor. Come to another one, the switch is closed at t is equal to 0 plus, find I0 plus di0 plus and d2I0 plus dt square because it is a RLC circuit. So RLC circuit is a second order system whereas RL and RC they are the first order system. So the switch is closed, so how will get it? So just we just write the equations for any time t. So when switch is closed, so inductor behaves as a open circuit and capacitor behaves as a short circuit. So at t is equal to 0 plus when the inductor behaves as open circuit, so I0 will be 0 because the circuit is opened. And this is the general equation for any time t. So 100 equal to L di upon dt Ri 1 by C I into dt, and there is no initial current through the inductor, so it is, so I0 is, so here V0 minus is 0. So this is the general equations. So at t is equal to 0 plus, at t is equal to 0 plus this I0 is 0, this is 0, so this is V 100 is equal to L di0 plus dt. So, di0 upon dt is 100 by L. So, this is 100 ampere per second because the value of L is 1 Henry. So, to find the d2I0 plus upon dt square, what we will do? We just differentiate equation first. So, this is L di upon dt square plus R di upon dt plus I upon C. Okay. Then put t is equal to 0 plus. So, t is equal to 0 plus. So, this will be this I0 is this is 0 and we have find the di0 plus dt. From here we can get the L di upon dt. So, this way we can get d2I0 plus dt square is minus R by L, which is minus 1000 ampere per second square. So, these are the way through which we can find the initial conditions or final conditions of any RL, RC or RLC network. One more problem, the switch is closed at t is equal to 0. Prior to closing of switch, there is no voltage across the capacitor. So, initial voltage across the capacitor is 0 and initial current through the inductor is also 0, and we have to find I1 0 plus I2 0 plus. So, these are the all initial currents conditions through the inductors and capacitors or through the circuit we can say. So, the switch is closed at t is equal to 0 plus. So, at t is equal to 0 plus, I0 plus is 0 because the inductor behaves as a open circuit and the capacitor behaves as a short circuit. Hence, the voltage across capacitor is 0. So, apply Kirchhoff's voltage law, KVL in this, this is the equation for any time t. Then at t is equal to 0, the circuit becomes like this. This inductor open circuit, capacitor short circuit, and we can find the I0 plus and I1 0 plus and I2 0 plus. So, I1 0 plus is V 0 plus upon R1 and I2 0 plus is 0. And from the second equation we can get the di2 0 plus upon dt, that is 0. So, to evaluate di1 0 upon dt, let us differentiate equation first. We get this, and putting all these value we can get the di1 upon di1 0 upon dt. And if I required to find the d2I1 0 plus upon dt, we again differentiate equation. Third, we can get the d2I1 upon 0 plus dt square. So, on simplification we can get the initial condition, that is d2I1 0 plus dt square. To evaluate d2I 0 plus dt square, we just differentiate equation second to get d2I 2 upon dt square, and on simplification we can get the d2I2 dt square. Now, come to the another problem, that is the switch is closed at t is equal to 0. Determine the voltage and currents at t is equal to 0 plus. So, at t is equal to 0 plus, the circuit becomes like this. Inductor behaves as a open circuit and capacitor behaves as a short circuit. So, we can find the I1 0 plus, that is 2 ampere, and V10, the voltage across 10 ohm resistor is 2 into 10, that is 20, and VL is 5 into 2. So, 10 volt. Because the voltage, this inductor voltage will be a voltage across this 5 ohms. So, this current through this is 2 ampere. So, 2 into 5, 10 volt. So, VL is 10 volt and this V10 is 20 volt. So, for the given circuit, initial conditions are VCY 0 plus 10 volts, IL 0 plus 0.5 ampere and VCX 0 plus is 0 volt. So, we can, this way we can find the VL. So, the important thing is just you have to draw the circuit at t is equal to 0 plus and t is equal to infinite, and then we on simplification we can get the initial conditions or final conditions for the given circuit. Similarly, for this circuit we can find the steady state voltage and currents, that is the V infinity and I infinity. We have to, so what we have to do, we have to draw the circuit at t is equal to infinity. So, at t is equal to infinity, capacitors behave as a open circuit and inductors behave as a short circuit, and once this is the circuit we can find the voltage and current. Simple sir. So, when we apply the conditions, initial condition behavior of the element at t is equal to 0 and t is equal to infinite, it is very easy to find the initial conditions. Okay. So, I stop here, and in the next class we will just carry out the network analysis using the Laplace transform. The circuit in the given circuit, initial conditions may be given or may not be. So, how will find the initial conditions? Those numericals I will take up in the next class. So, thank you. Jai Hind.